Hello guys, welcome back to another video on my channel. This is Gamma Di Gamma, your favorite YouTuber. Today I have an integral for you. It's going to be done by complex analysis. I figured let's do a contour integration since it's been, I think, at least 10 videos since we did another kind of integral like this. So let's get started. So I have for you this integral which I'll call I from 0 to infinity of ln x divided by x plus a over x plus b. Now, you may say, well, we can just do some partial fraction decomposition and then, take maybe differentiate, because the natural log comes from differentiating an exponential, we can maybe use or hope to use Feynman's technique. In this video, I thought I'd give you more of a direct proof. So note, throughout this video, a and b are going to be greater than 0. I will also talk of the case when either a or b is less than 0, and you'll see why we can't really achieve this kind of result when that case happens. First of all, let's recognize what f of z is. Since we're going to be integrating it on the complex plane, we should identify what the complex integrand is. In this case, f of z, where z is a complex number, is ln squared of z over z plus a z plus b. That's right. It's not a mistake that there's a square in the numerator. You'll see why in when we get to the calculations, why we need a square and not just, the original integrand itself. So this is the contour. We have region 1, which is going from basically this top part, which is very close to 0, and then going on to infinity. Then we loop back, which is region 2, end up on the other side of the branch cut. The branch cut is because of the natural log function at 0. So this is the branch cut from 0 to positive infinity. So when we're looping back, we end up on the other side of the branch cut, and then we zip back to the point that's near 0. And then we're looping around to join path 1, which that's integral 4, or path 4 rather. Now, one important thing I'd like to point out is that this path 1 and the x-axis has a distance of delta. So it's not just x. The points on path 1 are going to be x plus I times this delta. And obviously, we're going to take the delta to go to 0. Similarly with this bottom path as well. Okay. Fair enough. I hope the contour is clear and the procedure will follow naturally. Notice the poles are on the x-axis. The poles are minus a, minus b. So on path 1, the procedure is simple. Ideally, we should have x plus I delta for the delta height in the complex plane. But we can ignore that because that does not affect any of this kind of integral that we have. So integral f of z dz is equal to integral ln squared x, x plus a, x plus b, and the bounds of integration are actually from 0 to infinity. I mean, it's technically 0 to r, and then we're taking r to go to infinity. R is the radius of this infinite closure. But effectively, it's 0 to infinity. Let's call that I prime, because that's not the original integral I, it's just the squared or natural log squared version of it. Okay, so moving on to segment 2. Well, the segment, it's less of a segment, more of an infinite closure. So we have the natural parameterization z equals r e to the I theta, which is a circle of radius r centered at the origin. And of course, we're going to take the limit as r goes to infinity. So when I write that out, I have integral f of z dz equals integral 0 to 2 pi ln squared r e to the I theta divided by r e to the I theta plus a times r e to the I theta plus b r I e to the I theta d theta. Fair enough. Now we have to show that this goes to 0. So let's take the limit and then put absolute values around it. If we can show that this quantity in the absolute value after you take the limit is upper bounded by 0, then we can happily conclude that this integral goes to 0. Okay, so we have ln squared r e to the I theta over r e to the I theta plus a r e to the I theta plus b r I e to the I theta d theta. Now that's less than or equal to using the version of the triangle inequality that we normally use for integrals. So limit r e to the I theta 0 to 2 pi. So when I do that, I'm actually also taking the absolute value of r e to the I theta, which under absolute value will just give us r. So I'm going to write that inside the absolute value like that, alongside the ln squared r e to the I theta. And the denominator is as it is. I'm just applying absolute value to each factor in the denominator. Now, I'm going to use the property of logs that we can split up a product in the argument as a sum of logs. So ln squared of uv is actually ln of u plus ln of v squared. So when we square that with just the simple square algebraic identity, ln squared u plus 2 ln u ln v plus ln squared v. I just apply that, and I'm gonna change the denominator to its upper bound. So 1 over r e to the I theta plus a is upper bounded by the lowest value of r e to the I theta plus a, because since it's in the denominator, and that happens to be absolute value of r minus a. And similarly for this, we have absolute value of r minus b. They become the upper bounds of the entire thing because they're the lower bounds of the denominator. And we have an r and an ln squared r. We're just using this identity on the ln squared in the numerator. So when I do that and I take the absolute value, all the exponential terms will vanish. All the I factors will vanish. So ln squared r, and then we have 0 to 2 pi d theta, of course. That's the integral 2r ln r over r minus a r minus b theta d theta plus r over r minus a r plus minus b theta squared d theta. Now, the advantage of doing this was we don't have to take the limit. We don't have to argue for taking the limit inside this integral when we're evaluating it. Instead, we've just, by the means of upper bounds, we've actually taken all of r factors outside these integrals. And we can now show ln squared r over r minus a r minus b is actually going to be equal to 0 in each of these cases. The factors we have in terms of r are all going to 0 as r goes to infinity. These limits are not that hard to calculate. I leave that up to you. Now moving on. Segment 3 is actually the segment that's like segment 1 but on the other side of the branch cut, and we have to account for that in the sense our parameterization, instead of just being x or something like that, is going to be x times e to the I 2 pi. You might say this is just x, but then we need this in order for the branch cut to make sense for the natural log, because the natural log will actually split up nicely, because we can write ln squared of x times e to the I 2 pi as, again, the ln squared of a product identity that I've written in blue here. So that becomes ln squared of x plus I times 2 pi. So that's 4 pi ln x plus I 2 pi whole squared divided by x plus a, x plus b, where now it's just x because x times e to the I 2 pi is x, and x is not a multi-valued function, so this phase doesn't really make sense on x. So x plus b, fair enough. We have dx, and because we had the e to the I 2 pi dx, which is e to the I 2 pi is just one outside. So we're now going to have ln squared x divided by x plus a, x plus b. Let's call that I prime, because that indeed is I prime with a minus sign. The minus sign is because we need to flip the 0 to infinity bounds. Minus I 4 pi integral 0 to infinity ln x over x plus ax plus b dx. That's I. That's exactly the integral we want, along with this extra factor of I 4 pi. And we also get this additional integral 0 to infinity 4 pi squared over x plus ax plus b dx. Okay, now if we combine everything together in the entire expression for the loop, for this entire contour, it'll be a closed integral of f of z dz is going to be I prime minus I 4 pi I plus integral 0 to infinity 4 pi squared over x plus ax plus b dx. And we know from the residue theorem that all of that equals 2 pi I times the sum of residues of the integrand f of z on the poles of f of z. So and now I come back to the point I made, why we're using ln squared. It's because the I primes were the integrals which had the ln squared, and you see they're nicely canceling out. That's one good thing. And also, if we had used ln instead of ln squared, you would have noticed that in integral 3, that ln would have cancelled with the ln you got on step 1. As we see the I prime cancelling here. Instead of I prime, it would have been the integral we want, and that would have been really, really catastrophic for us. That would have meant that, the integrand choice we've made is wrong. So that's whenever you have a contour where you have to move to the other side of the branch cut of the natural log, assuming you have a natural log, always choose the square so that you don't accidentally destroy the natural log in the original integrand. I repeat myself, whenever you have a natural log and your contour is such that you start off on one side of the branch cut, you take a loop and you end up on the other side of the branch cut, almost like this keyhole contour. Then you want to take a natural log squared, because when you're on the other side of the natural log, you get an extra e to the I 2 pi factor, which expands out into a sum. And you don't want to accidentally annihilate your original integrand. That's why I take a square, so that when you expand the square, the ln squared cancels off when you sum them all together, and you are left with the original integral with the prefactor. So now let's find the residues. So residues, let's look at the poles. The poles, we have simple poles each at z equals minus a and z equals minus b. So when we take the residue z equals minus a, we're taking the limit as z goes to minus a of z plus a times f of z. So that's actually ln squared of minus a over b minus a. Residue of z equals minus b is going to be limit z goes to minus b of z plus b f of z, which is ln squared minus b over minus b plus a. So now if we write everything together, we can group them. 2 pi I times ln squared minus b minus ln squared minus a over a minus b. And then we just combine everything like this. Just a little bit of algebra more to do. So when I have a minus b here, I can actually take the principal value of that. So that means I can take b minus b as b times e to the I pi. It's called principal value because I pi is indeed the principal occurrence of -1. You could have taken minus I pi or 3 pi, any odd multiple of pi, and you would have said they're equivalent, but you were taking the principal value. I'm making that clear. Same with the a term, divided by a minus b. And then I'm going to expand it just like the a product in the arguments is expanded in the square. So I'm going to have natural log squared b plus 2i pi ln b minus ln squared a minus 2i pi ln a minus pi squared plus pi squared that come from the I pi whole squared terms in both the natural log expansions. So when I write that out, I get the imaginary term, which is 2 pi I times ln squared b minus ln squared a over a minus b, minus 4 pi squared ln b minus ln a over a minus b. So now I'm going to equate the imaginary term with the imaginary term of the white equation here. So the imaginary term, the only imaginary term in this equation is going to be minus I for pi capital I, because this integral beside it is all real, and the integral we started with is also real. So I that any real term times I for pi factor is going to be imaginary. So I grouped this imaginary term with the imaginary term I got out of the residue calculation. So that's 2 pi I ln squared b minus ln squared a over a minus b. And we have a minus I 4 pi times capital I here. So capital I is going to be 1/2 ln squared a minus ln squared b over a minus b. Fair enough. And that we know is integral 0 to infinity ln of x over x plus a x plus b dx. Now, you could say we're done here, but notice that if we group the real terms, so the real term here is minus 4 pi squared ln b minus ln a over a minus b, and the real term here in the blue equation is this mysterious integral that just exists here. So integral 0 to infinity 4 pi squared over x plus a x plus b dx. I call it an auxiliary integral. It's not a result of what we want to find, but more of a byproduct of the ln squared integrand choice that we made. Again, if you were to just group the imaginary parts and just forgotten about it, this wouldn't have been much of a bother. This is more of a side quest, more of an add-on to the procedure that we already have. So if I equate the real parts with each other, I get integral 0 to infinity dx over x plus a x plus b equals ln a minus ln b over a minus b, which you can also calculate using partial fraction decomposition. You can write this difference as ln of a over b over a minus b, and you can basically see how that emerges out of partial fraction decomposition. Now we can also take the limit as b goes to minus 1. So if we have that, will give us 1/2 limit b minus goes to minus 1 of the expression we had. If b goes to minus 1, we'll have minus b, or minus 1 is rather e to the I pi, the principal value. And we can expand that out to give us 1/2 ln squared a plus pi squared over a plus 1, because ln of 1 is 0. Now you might say, well, could we have actually done this using the contour integration ab initio from the start, from the scratch? Well, the answer to your question is no. If you try to do that, you run into all sorts of problems, and you need a more advanced version of complex analysis theory. The details get quite hairy, because what you notice, what happens, your branch cut was from 0 to infinity on the positive real axis. If you have b as minus 1, you have a pole on the real axis which is positive 1. So you have to basically jump around. You have to make the branch cut jump around the pole, and also the contour jump around the branch cut with an equal amount, and that is a very risky procedure. And there's no way of really putting your branch cut anywhere else, because if you put it on the negative real axis, you run into the minus a pole. You put it on the imaginary axis, you can't really close your integral off properly. You run into lots of issues there as well. So my recommendation is use the continuity. That is a way faster procedure. By taking the limit, we have to actually prove the continuity. I'm not doing it because, again, its details are too involved. We can also take the limit as a goes to 1. This limit is pretty harmless, because a was already greater than 0. So minus a was already on the negative axis. So we have a goes to 1 is a pretty harmless limit as opposed to the b. So we get ln of x over x plus 1 x minus 1, we can write as integral 0 to infinity ln x over x squared minus 1 dx. And that, according to the formula, well, if a goes to 1 ln squared, a is 1. We have 2 in the denominator and gives us pi squared over 4. So you see how the pi drops up. Pi comes about because we're taking one of these poles to lie on the positive real axis, and that's where the pi comes about, because the pi's had cancelled out if both of them were on the negative real axis. But in this case, if there's a difference, the pi will persist despite our best efforts and will show up eventually like this. So that's my time, guys. Thanks for watching. I hope you like, share, and subscribe to my channel, and stay tuned for more content. Peace out.